游戏接 Did you check? Yeah. Okay, before we start, let's talk about what you need to submit for your project. Since we've done our presentation, okay, so I will provide a cover page for you, okay, and then second is your project, right? Okay. And then third, I want you to put in your Turn-it-in report. I will assign you in. Okay, so for Turn-it-in report, right, after you submit, right, I don't want to see sentences. So basically highlight the sentences. Okay, so you should paraphrase them. Well, I mean, definition, theorem, that was unavoidable, so that's fine. But like proof and in anything you write down, please paraphrase them. Okay. And then if you think that your so the standard for FYP was 25% and less. Okay. So if you think that your percentage is still high after these, right? You should write more to increase your total, right? You should write more to increase your total. Okay, so meaning you need to write more, maybe paragraph explanation what you did, something like that. Okay. And then I want you to attach your Beamer slide also. Okay, at the back. Okay. And then lastly, I think is your progress report. Did I miss out anything else? Anything you think you need to include? Yeah. That's the thing. So you need to compile into a PDF when you submit. I will open up the link. Yeah. Sorry. Sorry. No. I said compile into a PDF. Yeah. So compile them into a PDF. So this one I will provide. And then I will assign you in. And then others you have to provide. Yeah, the report, right? So please give the full report. Don't give me a receipt. If you know what I mean. Any question? Any other question? Yeah, individual. Individual. Yeah, this is individual. Yes. Yeah. Individual. Okay, so this deadline is revision week, Monday. Okay, Monday or revision week. So next Monday. Okay. Any other question? Individual? No, no, no. Individual. Yeah, submit your own project. So yeah, 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 your own thing. What's appendix? No, no, you have your own topic, or you speak like in your reference your paper. Yeah, yeah, yeah. So you name your paper as I think should be similar to your uh yeah title, right? Yeah, yeah, top title. Yeah. Okay. Any other question? I will make the tab for this. I will include this in also, and then I make a submission line link. Yes. Theorem is fine. Yeah. But there's one problem is all if all your definition theorem get highlighted, then one possible case is your percentage is very high. So one way to reduce it is you have to write more for your content. Yeah. So meaning you need to increase your total. Yeah. So that you can reduce your numerator. Okay. And then I want this to less than 10 pages. If you are more than 10, I will um, penalize you. Okay. So if there's something that we really cannot miss, for example, let's say, let me give an example. For example, for example, Joel, right? Okay, so Joel used a lot of representation theory, but I don't require you to prove it or what. You just use that definition or theorem. So if you think that, oh, this part I must include so that my main body makes sense, but I'm not going to prove it. What can you do? Instead, actually, you can put it in the appendix. Okay, I'm not going to check that as well. It's just to facilitate reading. Yes, yes. And also the appendix won't count as your real content. Yeah, 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 yeah. You are not gonna prove it. You're not gonna okay, yeah, not gonna prove it. So you can put those extra stuff as your appendix. Yeah. So the main accessible content will be your like the body as the body, what you have learned, what you have produced, and what you demonstrate that you use algebraic geometry stuff. Yeah, make sense? Yeah, 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 yeah. For the last, yeah, this is the weekly progress report attached at the back. Last week we discussed what should be included here, right? Yeah, attached as the last. So this, all these, you need to compile into a PDF. Submit. Okay, any other question? Yes. No conclusion. I don't require to write conclusion. I write it in my course info already. Everything up to before referencing. Abstract intro and then body. I think that's it. Anything else? Okay, so for the leaders, please inform your member. Some of your member like to skip class. Okay, so please help to inform them. Is all the leader here now? 2, 3, 4 up here. Yeah. Okay, please inform them. Okay. Okay, so this is about project. Okay, another thing is so if you notice, so for those who stay to the end, right? We got a visitor from Imperial College London. So he is a graduate, undergraduate actually. He's also just doing 3 years undergraduate. And so he's coming to give a kind of a public lecture or introductory talk to Morse theory. Maybe you can come on this Wednesday, 6 to 7. I think 6 to 7. Yeah, I think student council will be making the promotion soon. Yeah, but basically 6 to 7 is the study group room. I think it's A4G11. Yeah. Okay, so please come and maybe we can talk some maths with him. Yeah, what kind of pure maths he's doing. He's gonna, I think if successful, he will gonna do part 3 in Cambridge for masters in this coming September. Okay. Anything else I need to update here? Anything you want to ask me? Oh, okay. So we are like finish up, right? So the last few things we do is Riemann Roch. We're not gonna prove it. We just introduce it, and then I will do something called ample divisor. And these tools are very important when you go further in algebraic geometry. Okay, although we don't test it in this class. And then so for tomorrow, tomorrow plan was if we can finish the thing that I want to say earlier, then we could talk about assignments 3 and 4, discuss about the solution, and then if can, maybe I will return you assignment 3 by tomorrow. If can. So and then if still got time, maybe we can discuss about the last assignment if you have question about it. Yeah. And then anything else? Oh yeah, one last thing. So how about revision class? Do you guys still want it? Or you can you revise yourself. What do you think? So the final exam material will be up to projective variety, everything before what do you call it? Smooth point. Yeah. Okay, so yes. Sorry. Shift structure. Yeah, sure. I mean, do you need a revision class? This is my question. Yeah. Do you need? Huh? I'm asking you. Huh? You cannot come back. You can online only. Okay. How about the rest? Huh? What do you think? If we're gonna make revision, there must be someone physical. Okay, cannot be a full online. You can be physical. Okay. So our exam is on Wednesday or Thursday? I remember. Thursday. Huh? So how about revision week Thursday? So it'll be the day after you submit your assignment. Yeah. Yeah. Revision week Thursday. Yeah. So it'll be the day after you submit your assignment. Okay. Maybe afternoon, 2 to 4. Okay. So during this revision week, right? Try the revision class. Try to do the tutorial before you come. Okay, and then you prepare question for me. Okay, I will answer, and then we can discuss. And if I have any tips, I can told you also on the day. Yeah, but please do try and revise first before you come, and then you bring question, and then we can discuss. Okay. The location I will tell you again. I think I will be booking the meeting. Should be enough for you. Okay. During the revision week, it's also hard to book room because they use it for exam. Yeah. Okay. Sure. Okay. And I think I do a promotion on the FYP for general topology. But in this class, I think some of you are also 2309, right? So you're gonna do FYP next semester, correct? Yeah. So I'm holding a FYP recruitment drive. Recruitment drive. So if you could come on Friday 4 to 5 like that. Yeah. Okay. We can. I mean, I can try and offer some topics. Yeah. So that you can listen or you want to give some suggestion. That will be after general topology revision class. Yeah. Okay. Mm-hmm. Yes. 4 to 5. Yes. Because 2 to 4 we got general topology revision class. So we'll do it after that. Yeah. As most of the 2309 will be there also. Next revision week. Okay. Okay, I will put the details on Moodle also later. Okay, so let's continue with the final thing we're gonna talk, which is Riemann Roch theorem. Right. So, what do we need for Riemann Roch theorem here? So, first we'll define a partial order on devices. Okay, so how are we gonna compare two devices? We can't really compare about points, right? How do you like give an order to the point? But let's say these two devices here have multiplicity on the same point that can be compared. Then what we compare will be their coefficient. Okay, so we said that D1 is greater or equal to D2 if and only if NP greater than NP for all P. So if you can compare, because the coefficient you can compare, right, there are something in Z. Okay, so if one set of the coefficient is greater or equal to the other set, then you can have a partial order of them. Then we'll define this particular set here. This set here will play an important role in the Riemann Roch theorem. So fix a divisor. Then we'll define LD, this capital LD here, to be all the f or the regular function, such that the principal divisor defined by this f here is greater or equals to negative of d. Or you can think of it as this principal divisor plus d greater than equal to union 0. So principal divisor plus this divisor greater or equal to 0, meaning is greater or equal to the divisor with coefficient all 0, right? And somehow you add to the d such that um, the pole disappear. If you can think like that, okay, because greater or equal to 0. So meaning your coefficient must be all greater or equal to 0. Okay, so there's no pole. Okay. So one thing you can show that is, let me remark here, this LD is a K vector space. Okay, this LD here is a vector space. Well, you see 0 is in there already. Maybe you can show the closure under addition, and closure under scalar. Because scalar is a unit, right? You don't really change the order of 0. Okay? And then if two of them satisfy this partial order, then the addition of them should satisfy. And then next, I will define that the little d, okay, little ld, sorry, is actually the dimension of this vector space. Okay? Not that d might not come from function, meaning this d might not be a principal divisor. But you look at all the principal divisor that when you add to d, the coefficient is always greater or equal to 0. Okay, so in the notes, I think I attached some examples. Should we try some examples? Okay, how about we try some examples so that you have some idea. So let's say consider the curve T1. Okay, and then let's say we look at D to be the point 1, 0 at 0, 1. Okay, can you try and show that this regular function here actually live in L? Yeah, let you try maybe 2 to 3 minutes. Okay, so to turn this regular function into divisor, you should figure out what's the 0, what's the pole, and what's the multiplicity. Okay, anyone try? So let's call this F. Hi Larry, what do you think? What are the zeros here? What xy make this function to 0? X equals x equal what? S equal y. S equal y. Sorry, but this is P1, right? So what is the line that this line correspond to? 1, 1. Okay, one of it is 1, 1. Order 1, right? Because the multiplicity is just 1. What else? 1 minus 1 is another line, which is another point in P1. Okay, so these are the zeros. How about the poles? So you want to make the denominator 0. Okay, so one of it is 0, 1. So it's poles, right? So you take to negative. And then the other one, 1, 0. Okay, so this is the divisor. So you want to ask whether if you take this divisor add to D, whether it's greater or equal to 0 or not. You just compute it. df plus D, right? What do you get? You get 1, 1 plus 1 minus 1. So the coefficient is all greater or equal to 0. So this is giving in LD. Okay, so this f is living in LD. I think this f is not our notation. Our notation is like this. Sometimes book also put if f. Okay, okay. So the coefficient are all greater than 0, so it's living in LD. Okay, makes sense. Okay, so anything else I need to show you? Okay, I think this is the thing that I want you to know about device. Okay, so let's see what we can do with it. Okay, next, we're going to define what's called a support. Yeah, so you can see that obviously we can take coefficient to be 0 at any point, but that's meaningless, right? So we'll say that the support of a divisor is actually defined by, okay, who are the support of a divisor? Okay, basically these are the point in your curve such that the coefficient is non-zero. Okay, so support, you can support your divisor. Then we will call that a divisor is effective. Okay. It's called effective. Sorry, it's called effective if the D is greater than or equal to 0. Okay, so meaning all the coefficients greater than 0. Okay, we'll call it effective. So there's some lemma here. So if the degree D is less than 0, okay, then we will see that actually LD is just consists of 0 divised. Okay. Second, okay, for every effective divisor here, the effective, so we actually have that. We can relate the dimension of LD to its degree. Okay, so LD is less than or equals to degree D plus 1. Okay, so we're trying to relate the dimension of the vector space LD to the degree of D divisor. So degree of divisor is just add up all the multiplicity. Okay, so in particular, this actually shows that LD here is a finite dimensional vector space. Okay, because last time we showed that the divisor will intersect finitely at finitely many points, right? Okay. So you won't have like infinite sum. Okay, so you add up all the degrees, just a finite number. So LD here is a finite dimensional vector space. And when do you get equality here? So you get equality only if C is rational. Rational means isomorphic to projective space or affine space. In this case, it should be projective. Or D equals to 0. So if D equals 0, then that means the LD you define is just one dimension. So these are the two. So let's prove it. The proof is not very difficult. Shall we prove it? This one. For this one, so if degree of D is less than 0 and F is an LD, okay, what happened here? Then if you add F to D, we want it to be greater or equal to 0. So because the degree of D is less than 0, right? So D should you should cancel out the negative part. But how to cancel out the negative part? You need to have the positive part, right? But the positive part in F correspond to what? The multiplicity of 0. Okay, so this means that F must have more zeros than poles. Okay, more zero than poles. Could it be possible or not? F define a principal divisor. But what do we talk about principal divisor last time? Every principal divisor have degree. Degree what? Principal divisor. Yes, we use it to prove the Bezout theorem, right? Okay, so it must have degree 0. So if you have more 0 than your poles, then it will contradict that your degree is 0. Because the number should be the same so that they can cancel, right? The positive part and negative part should be the same. Okay, so meaning this 0 that can satisfy this. So in that case, the interesting D such that LD is interesting is when D is when degree of D is positive. Okay. If less than 0, then not very interesting. Okay, how about the other case? Okay, so the only two things we should consider here. So one case is okay, one of the case is the degree of D is 0. Okay. So case one. So let me put case one here. Case one is degree of D is 0. Okay. So since degree of D is 0, but we also know that D is effective. Okay, so meaning we have D equals 0. Sorry, since D is effective, we have D equals 0 as NP must be greater or equal to 0 for P. Okay. Because your effective meaning your coefficient must be non-negative, right? But how can you like add non-negative stuff together to get 0? The only possible way is all of them is 0. Okay, make sense? Okay, so actually D is 0, but in this case here, what do you get for LD? But in this case, what is your LD here? Okay, so your LD is basically the space of constant. Okay, so your LD is basically a space of constant. Okay, so if you consider definition back here, right? Okay, so my LD is here. So your D is 0, so meaning your principal divisor here must be greater than 0. Okay, and then the claim here is the only f you can put here is is constant. Does it make sense? Does it make sense? If d is 0, then the f here is constant. Does it make sense? I think, so if your f got if your f has non-zero, I mean have zeros, right? Doesn't it still satisfy it? Did I miss out anything? Yeah, so is everyone getting this claim or not? Let me see. All right. D is degree 0, then since D is effective, then D is 0. In this case here, D is the space of constant. Does this make sense? Seems like doesn't make sense. LD become some principal divisor greater or equal to 0. Right. Yeah. Sure. Sure. F have to be a polynomial first. What do you mean by degree 0? Mm-hmm. Mm-hmm. Degree of the divisor is 0, yeah. But this is LD, right? LD is the thing that add to this divisor, you get greater or equal to 0. Sorry? Yeah, first we have outpost, yeah. Mm-hmm. Again, play the same trick, huh? Again, we play the same trick, right? So because this is the principal divisor again, right? So we want it to be greater or equal to 0. And then, wait, yeah. And then principal divisor again have degree 0. If you just simply add 0 in, you cannot cancel your degree to 0. So your number of 0 should be also 0. So it should be a unit. So there's a constant. Okay, makes sense. So again, so we say that again, play trick. So use the claim degree of principal divisor is 0. Okay, so from here then from here, we should see that LD is just one dimension because it's just a constant type one. Okay, so how about case 2? Okay, let's talk about case 2 here. So the inequality satisfied, okay, because 1 is less than or equal to 0 plus 1. Okay. How about case 2? Case 2, let's suppose that, let's call it D now, the degree of D is greater or equal to 1. So let's play this game. So we will let P1 up to PD plus 1. Okay, one more point than the degree of D. Be distinct points that do not lie in the support D. Okay, do not lie in the support of P. Okay, then what we can do was we take L of D minus P1 out to P. Okay, so we can choose this point because I think our field is algebraically close. This one is infinite. And then the intersection of D with the curve should be finite. And so we should be able to pick points. And then we will look at this specific divisor here. So L of D minus this thing. Okay, so how to understand this? Well, the claim is if you look at the set of this LD here, D minus this bunch of points, actually this is basically equal to the kernel of the particular map. Later you'll see why we will term it as a kernel here to facilitate explanation later. But let me write down this map here. So this map is evaluating this F inside the set on this PD, so D minus 1 point. Okay. Okay. Makes sense. Do you make sense of the negative sign here, positive sign? Yeah, because this negative is act as a pole, right? So your function should have a 0 on those things so that they can cancel. Okay, so that's why your app has 0 at P1, not D plus 1. Okay, makes sense? Okay, because in the definition of L, right, you need to have your principal divisor add to this bunch of things. But this, if you put your point as a negative, meaning it's like a pole zone. So if you want it to be greater than 0, then your F should have 0 on this thing. Okay. Well, so if you look at this definition here, so this means that L of dp, so this is a very nice way to see what is the dimension of this. What could this dimension be? Yeah, what could this dimension be? So this dimension, instead of talking about this dimension, we can talk about the whole dimension. If you like the dimension, you just take the full dimension and take it away. So the core dimension here must be at most d plus. How about us, Eric? How to turn this core dimension language to dimension? If I say core dimension must be at most d plus 1. So meaning like what should the dimension be? The core dimension is at most d plus 1. So what does the dimension do? So who minus who? The whole space. So what's the whole dimension here? What's the total dimension here? Do we know the total dimension here? It's also d plus 1. D plus 1, right? Okay. Sorry? At most, at most, at most. Okay, could be less. Yeah, could be less. think of everything go to everything gets sent to kernel or let's think go to the okay. But however, what can we mention about this L of d minus d plus 1 point here? I purposely put one more point than the degree of d, right? So if you take away d plus 1 from d, what do you get? You get minus 1. So which is a negative degree. Okay, so in the previous previous point, we proved that if the divisor have degree negative, this means that this set is actually a self-zero. Okay. So we can see that L of dimension of LD is actually less than or equal to 2 plus 1. Okay. Which is equals to a degree of E plus 1. Make sense? Yeah, what does this co-dimension is? Ask you. Last time, how we define co-dimension? For example, a line is a co-dimension 1 in dimension 2 space, for example. So it's actually dimension 1. It's also co-dimension 1. Okay, co-dimension 1 is just take the total dimension of the space minus the dimension of that particular space. So 2 minus 1. Okay, so for example, hypersurface. Right. So hypersurface is generally a dimension of the total space minus 1. So it's always co-dimension 1. Okay, instead of talking about the whole space, take away 1, we just talk about, oh, it's co-dimension 1. So we'll know that, oh, we need to take the total space and then take out 1. But here, what's the total space here? What's the total space here? I say it's a kernel of this map, right? So it should live in LD, right? Huh? It should live in LD. Okay. But we have a map. We map this kernel. We map this F into a space of KD plus 1, right? Okay, then. Rank theorem says what? D plus 1 equals to the image plus kernel. Let me think. Does that work for surjective only? Anything else can make sense or not? D equals to the image plus kernel. You don't need surjectivity there. Rank theorem. Yeah, rank theorem don't need subjectivity or why? Huh? Okay. Why rank theorem no need subjectivity? Okay. So rank theorem basically is just decomposing the domain, not the codomain. Yeah, it's just split dimension of codomain into image and kernel. Okay, but the image, sorry. Yeah, it's the domain. Yes, yes, yes. So it's not a codomain. So definitely you would know that something is called the image, something is staying, and something is sent to the kernel. So in this case here, we have the same thing also. We split LD into the kernel part and the image part. Okay, so the dimension of image will become the co-dimension of the dimension of the kernel. Okay, so this co-dimension is really talk about uh, how big your image could be. But we term it as a co-dimensional because it is the counterpart of the dimension of your kernel. Okay, co-dimension. Because we really cannot talk about what's the dimension of LD. We don't know what is the dimension of LD. So that's why we don't want to talk about dimension of LD minus, that's what, D minus 1. Like that. So instead of talking about dimension of LD, we can say co-dimension. Make sense? Okay. 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 Yeah, but since we know that the nullity says that dimension of LD equals to the dimension of the kernel, so L of this D minus P1, blah, 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 plus the dimension, so co-dimension of it, right? This whole thing here. Okay. Oh, okay. So you should check that this F will stay inside this LD here. So just check this. And then everything in this LD set here is a kernel of D. You should check this. Yeah. So how to check kernel? You need to evaluate to 0. Yeah, you should check that. Okay. So basically, if you want to stay in this set here, this point here already partially express your principal divisor already. And then those part will help you to talk about evaluating to 0. Okay. And then if you're gonna evaluate to 0 at this point, right, meaning your divisor should contain 0 on those 0 factor on those points. So it should be something living here. If you have something living in here, your function should be partially expressed as a factor of 0 using this PI. Then you should evaluate to 0. Okay, so this is what you need to show. Okay, make sense? Okay, so this KD plus 1 here is will help us to talk about the language of dimension E. Yeah. Any other question? Question? Okay. Oh. So we are left to prove the equality section, right? So now, so let's suppose that LD is actually equals to D plus 1. Okay, let's prove the equality case. So if this is equal to D plus 1 means what? Means that actually the map we consider just now is an injective map. We can reach the whole space. Okay. So implies that the map just now is actually surjective. Surjective. Okay, so we can reach the whole D+1 vector space, dimensional D vector space. Okay, but we play a trick here. So then, since you are surjective on KD+1, how about just look at the projection onto the first D-1 component. Okay. So this composition here should also surjective. Okay, so meaning the kernel that we are looking at now is a new kernel. So LD minus P1 minus up to PD. So okay. So let's say we just now we got KD+1, right? So now we reduce to KD-1. Okay, restrict to the first D-1. The claim here is still surjective. Okay, so we look at the first KD-1. Okay, still subjective. Make sense or not? I just reduce the range. Okay, you can reach the KD+1. Obviously, you should be able to reach KD-1. Okay. Thus what? Thus the dimension of L dp-1 L d minus P1 minus out to PD-1 here. What's this dimension? And so this dimension should be should be what? Let me see. So the claim here is this is D+1 minus D-1. Let me see, makes sense or not. Okay, so does this make sense? Does this make sense? Okay, what we have now here is the previous KD+1. Okay, now I subject to KD-1. Okay, so what's the difference here? The difference here should be covered by your kernel, right? This whole thing should send to 0. Okay, otherwise your dimension cannot be KD-1. Okay, so these are the things that get sent to 0. Okay, and then we identify like how we did just now that this should be the kernel of this composition map. Okay. Because we cannot remember, I cannot say that this D is degree 0 anymore, right? We're not sure whether it's degree less than 0 or not. Because this D-1 already less than D. So I cannot use the same argument that we have just cannot apply. Okay, so dimension 2 means what? It means that they are linearly independent function inside this L here. We call it FG. D minus P1. So, okay. So since degree of D minus P1 minus out to PD-1, okay, so we could count this degree, right? So it just add up all the coefficient. So we basically have D-1. Okay, this -1, D-1 -1 sign. Okay, and then the degree of D is D. We define it. So the degree of this divisor is this one. What does this imply? The degree of this is equals to what? Okay, so meaning F and G are degree one stuff. Okay, they are degree one stuff. So if our degree one stuff, what can we write it as? So it follows that F, the principal divisor F would be P1 plus out to PD minus 1 minus D plus extra point. Okay? And then because F and G are linearly independent, so we could add another point, okay, to this G here. Okay, so such that P and Q is different. Okay. But not that P and Q are actually equivalents, linearly equivalents, because you can write down a function that vanish at F, and then what do you need to show equivalence? Vanish at F, and then take a pose in Q, right? Easily in our case, right? Because we are projecting. Make sense? Does it make sense? Does it make sense? Simply take 2 points equivalent, because you can write down a function that vanish at P and then go take a pole at Q. P minus Q is a principal optimizing. Okay, good. Okay, so in this case here, F over G here actually live inside KC. F over G here actually live inside KC. Okay, and then we claim that this map actually is a birational map, which induce an isomorphism that give you the isomorphism to show that C is isomorphic to P. So actually this is a birational. Okay, okay, right. Okay, how about the other direction? Let's say you know that it's rational. Okay, if C is rational, then we can always find a rational function with poles counted with the multiplicity given by the divisor D and 0 at exactly D of the point P1 up to PD minus 1. Okay, so what does this mean? This means that if you map this rational function across to a KD plus 1, then this map is actually surjective. Okay. Okay. Any question? Any question? So remember, this map is just an evaluation map. Evaluate at P1 up to PD plus 1. Okay, any question? No? Okay, if no question, how about let's take a break here. Let's break until 115. 115. 你3月跟之前你们没有教你们 FYP 的东西是吗？今天要教，因为呀，今天是最后一天，你们的那个 correction 还有你们的 progress report。哦，还有你们的 turning in similarity report 也是要3个模式。有人知道进宝几时回来吗？不知道，还没跟你讲。那他为什么要请到？因为要符合整个 proof 啊。
为什么？我只要 break 其中一个 part，为什么要全死了其他的？
因为会不会有一个可能性是，他有了前面那个 part 过后，这个 part 就永远对的，你懂我意思吗？
那这
就是说，
里面需要找一个 compactor，但是不是一个
对，没有错，其实就是在问，对，他的考来 example 其实蛮难的，所以我没有拿掉很多分。
有人答对吗？
呃，有人找到难的啊，呀，他没有，他 obviously 有了，I mean 有，I mean 我给你们那本书里面有，但是看你看不懂，好吧？呀，有一点抽象版，所以说你要再讲。就像他们啊，还有一点，这边这边做饭的这边我发现他说，关键你关是啊，基础性，我在看你这他有超会，这么因为你 report 印出来还是只是个地方是，这个是有画，这个有画，那你就拿这个就来这个分开，因为这个可能是你自己的嘛，他是 scan 到你之前交的那种。如果那份 report 上面显示是一个这样版的，因为之前金宝那全是多的。
有点没理解。我现在每一个 logical 的 chain 能打破一个，
你没有打破那个话，因为它可能如果 compact 加上他讲的东西，可能会打开。 那个 f 那个东西，你现在是只是把那一环来，那一环它其实还有包含 compact 的条件的，你明白吗？
明白？
你只是没有写下来罢了。其实你一直在 assume 你在一个 compact 的，你漏了一个东西。这样对，它因为也
OK，
就是如果我的它有 PE，就是 MEP 加上 LP 的话，那么这个 LP 其实它就会等于就
欧这种情况，
上就是那个视频的，就讲的就是除了在 PE 之外都 regular 啊，分母只能是就讲它的分母都只能是 x 点 PE 的 a 次方乘上 x 点是吧？它是属于这个生或者是一个可能是 S 那个 curve，然后这一个是好像一个 multiplicative subset，那这个 subset 呢是 generated by x 减 p x 减 p 的。因为你的这个 LD 里面所有的
不可以给
因为 LD 所有的方向都有至少要 x 减 p 的多少次方，x 减 p 的多少次方，所以它其实就是在这一个 subset。
那是一个东西加上那个你说它是要要求一个跟你这个我的我是哦，这以外的东西是我觉得在里面还是等于它，
啊，在里面，不能在里面，不在。
我觉得是，但是这个也是在里面吧？我觉得这个是这个等于，
这个应该是等于的。可是我上确定一讲它不等于，他讲说不定他讲他好吗？说不定有一个是 y 点 q，然后在 x 等于 p 的时候 y 点 q 等于零。然后那个 ChatGPT 跟我回答那个东西，我不明白，应该是在不是 algebraic 那个 k 不是一个 algebraic 的 field，
这个 make sense，这个是一个 algebraic。
这一个这是个开题，就是那个 curve 上面除了 p 和 p 二之外的啊，这个不好意思，写到这个字
这样 make sense，但这个就 make sense，这不是 structure sheet 吧？这个只是一个 local，structure
对，
把这个东西比较少。
好，
然后这个
这种
如果它是整个 C 的话，这个 global section，然后如果你应该要这边画 C 切掉这个内容。
我是讲它的分母就是由这两个组成的 multiplicative subset。
这个 T 不是 T 以外的东西，是不是太容易了？这个 T 以外的东西不是。
是 t 以外一个分 t，如果放 prime 掉的话是，但如果你放那个 general multiplicative subset 的话，是哦，因为我没有打算 t 放 prime，我 t 放一个 multiplicative subset。
OK，对啊，OK，嗯，如果你要说这个跟这个肯定，
这我能确认一下我想的东西对不对？因为我看到这一个其实就是属于这一边里面的元素了。
不合理。然后这个跟这个
应该我的直觉跟我讲是一样的啊，因为你在这两个点，然后有了知道你这两个是分母，你在这两个点弄来就那两个东西是分母的，应该是一样的。
我想嘛，对啊，不写这种。 写下来这样发给我，他想一下。对，这个感觉应该是对的。但是这一个的话，加另外这个，先写下来那个 statement，然后再审一下。Hello, testing. Okay, right. Okay. Next proposition is if we know that D1 and D2 are equivalents, linear equivalents, or meaning D1 minus D2 is a principal divisor, then actually these two vector space is also isomorphic. Okay, so the proof is really not too long. So if they are equivalents, then meaning you can write down the principal divisor. Okay, so well, how to construct the isomorphism? So you need to tell me where to send the elements. So let's get a G out of LD1 first. Then we will use this F here. Okay, so how we're going to use this F here? So we will basically consider GF. Okay, consider GF here. So what is the divisor of GF? Okay, so basically it's divisor of G plus divisor of F. Okay, because it's multiplicative. Basically, it's just the multiplicative. Can I say it's a multiplicative? No, not about multiplicative. It's a homomorphism, right? The new, still remember the new fg equals to new f plus new g. Okay, so if you write down you count the divisor, actually you are counting the factor, right? Factor in the numerator and denominator. Because GF multiply together, so the factor add up. So it's additive on the separate component. But we know that G is greater or equals to D minus D minus 1. Sorry, minus D1. Okay, but minus D1 plus F, what is that? Okay, F has a relation between D1 and D2, right? So you really get minus D2. So actually, this GF here, the divisor defined by GF, live inside LD2. Okay, what's left to show is to show that this is an isomorphism. Okay, shouldn't be hard. I can show that this is isomorphism. Okay, so meaning this linear equivalence, right, help you to build a bridge in between these two vector space here. Okay, LD1 and LD2. Again, by multiplication. Okay, that makes sense? Okay. Right. Another thing we need to discuss is called a complete linear system here. Okay, what's a complete linear system here? We write it as a modulus. So it will make sense when you see a definition why we put modulus there. Because it is really taking all the effective divisor. Okay, so it's like make it positive. Okay, such that what? Such that all these divisors should be linearly equivalent to D. So meaning all the effective divisor that is minus D, you get a principal divisor. Make sense? Okay, so another word here is you are collecting all the D prime, okay, all the effective divisors such that the L of the D prime is isomorphic to the L of D. Okay, make sense? So you are trying to find an effective divisor counterpart. Okay, so that's why we put modulus. Some modulus is make it into the positive part. Right? Okay, so remark here, if degree of D is negative, can you still find a positive counterpart? Okay, since equivalent divisor have the same degree and principal divisor have only degree 0, so no one really can bring you to a positive part. And the effective divisor have a non-negative degree, so this set is actually an empty set. Okay? Because you want to equivalent to something degree 0, you are negative. The degree 0 can't help you to bring to negative, positive, right? Okay, so there's nothing here. Okay, so it's not like our number, right? modulus of negative x, maybe you still get x, but here no. Okay, here no. Okay, make sense? So in this case, basically what we are considering here is just we are collecting bunch of equivalence vector space, okay, that defined by equivalence divisor. Okay, equivalent positive divisor. And we don't want negative one, right? We don't want the negative one. We want the positive one. Then maybe a negative one also equivalence, but we don't. Okay. So there's some other property here. So there's one very interesting property here. There's a natural bijection. Okay, bijection between a complete linear system with the projective space. Okay, projectivized LD one here. This one is quite interesting. So remember, we have a vector space. We can projectivize it. You just consider all the lines. Okay, is that a point? And then really, you can send every point in this complete linear system here to some line. Okay, some line inside your vector space. Okay, this one is pretty interesting. So let's see what we do here. Let's see what we do here. Where's the line? Let's see. Okay, the line is here. Okay, so where's the line here? Where's the projective structure? So you should ask yourself, where's the projective structure in PLD here? Okay, so the vector there is some function in LD, right? So if you look at the scalar multiple of F, that should define the same divisor, because this unit here won't contribute to any zero or poles. All right, so this is the projective structure there. Okay, makes sense. Okay, so how do you send a divisor in LD to complete a linear system here? You consider this divisor of F plus T. That's it. Okay. Divisor of F plus T. And then you need to show surjectivity and injectivity. Make sense? Yes. What is lambda? What is lambda? Oh, what is lambda? Okay, sorry, this should be the notation of live inside. Okay, thank you. Oh, and also our K is above K, right? So you can see that if I set it to be F plus D, right, then this thing minus D is what? Is F is a principal device. So it's equivalent to D. Okay. Yeah, this is the thing that equivalent to D, because if you take F plus D minus D, what do you get? Exactly the principal device. So this is equivalent to D. Yeah, then you need to check surjectivity and injectivity. Okay, makes sense? Yeah, so the projective structure is here. Okay, so one thing you very important concept in this topic here is the unit won't affect your number of 0 and 4, right? Because unit is a constant, right? There's no 0. No 0, right? Constant, right? 1. No 0. No poles also. Okay. Obviously, I'm talking about non-zero unit. 0 is not unique, so okay. Okay, and then that's the complete linear system. Okay, we look at all the possible effective divisor. But then if we just consider a projective subspace of a complete linear system, then we will call it a linear system. Okay, it's just a subset, right? Linear system, projective subspace. And then another thing is a point in C, we call it the base point of a linear system if your linear system is equals to the linear system intercept with the complete linear system of V minus P. So it's like you take away. Okay, so let's say so let's talk about the full complete linear system case. Okay, let's say this is D, this is D. Okay, so this is D. What does this mean, sir? What does this mean here? Let's say we talk about complete linear system. D intercept D minus P is D. So meaning what? You take away P doesn't really affect. Okay, doesn't really affect to getting back your D. Okay, so a linear system V is called base point free and no base point if it has no base point. Yeah, base point free. So meaning there's no P that can give you this property. It's like you take away a point, it seems like you did nothing. So meaning if your linear system is base point free, right? Meaning if you take away 1 point, you won't get this equality anymore. Okay. Make sense? Okay. Right. So let's see how to put these things together. Okay, so there's a remark here. Okay, so like what we do just now. Not that if we have a complete linear system equals to complete linear system intersect with another complete linear system take away a point, then this would actually implies that D and D minus P is linearly equivalent. Okay. Okay. So how to get from a system that have a base point to a base point free? Basically, you just take the system, slowly take away the base point. Okay, D minus all the P. And then we will get a base point free. Okay. So from now on, we will just consider base point free linear system. Okay. We won't have a system that you take away a point, you still get back the same thing. Okay. So this is another setup before we go to Riemann Roch. So this is a bit of a different thing that we did for divisor. So for each open set U here, if you have learned differential manifold, maybe this is a very related stuff. So for each open set U here, what we consider is a vector space 5U. Okay, so such that another phi here, bar phi of U to the union of this tangent space. Okay, so this is this, wait, let me think. Which one is a cotangent? Which one is a tangent space? Let me think. I think this is a tangent space, right? This is the Zariski tangent space. Is it cotangent space should be a one with star? Is it how I call it? So okay. So our original tangent space was defined using the linear parts, right? So the first partial derivative. And then we prove that this is isomorphic to what? Mx over mx square star or without star? Star or without star? Can you check the note? Star or without star? The star or without star? Right. Did you find it? Star or without star? Hmm? Okay, so this is our definition here. So MP over MP star here is called the Zariski tangent space. So this is where we prove isomorphism to the linear part that we defined. But so MP over MP square is the Zariski cotangent space because star and without star is dual to each other. Okay, so one of this cos dual space. So we call it a cotangent space. Okay, so let's come back to here again. So what we look at is actually the union of cotangent space here. So this is kind of playing a role of tangent space in the differential manifold. Okay, so what is 5x here? 5x here is something in mx over mx squared. Okay, you map to some element inside here. Okay, so last time we see that when our curve is when our variety is a curve, right? If a projective dimension 1 curve, then actually this mx over mx squared is just dimension 1. And so there's really only one thing up to scalar you can pick from here. Okay. Then for a regular function f in the local ring here, OC applied to U, what we get is we can define a element, okay, in 5U here. Okay, we call it df. Okay, this df actually is really the calculus df that you have seen before. Okay, but this is the algebraic version. Okay, so in a complex case, there should coincide. Okay, what we do is, it's not a derivative. We are not telling you to do the first principle stuff, but this will serve what it happens in derivative. So what you do is basically f minus fx first. When you differentiate, your constant also disappear, right? Okay, so here also make the constant disappear first. But where is the derivative left? So the derivative happen at the mod there, mod mx squared. Okay, mod, so you can get rid of something inside mx squared. Okay. Okay. Or replace with something easier. Do you remember quotient ring? You can replace with something easier. Okay, I'm not going to comment much. I'll let you to imagine. So, for example, you can prove the Leibniz rule. So, okay, similar to the chain rule, product rule. You can prove it, okay, using this algebraic definition of df here. Okay, you can prove that df plus g actually is df plus dg. This is the product. Yeah, no, this is some rule, okay, in differentiation. And then you can prove the Leibniz rule or the product rule, dfg equals to fdg plus g df. Everything is mod m square x. If not mod, they won't be equal. You have to mod it. Three, quotient rule. Okay, you will get quotient rule also. And then 4 would be applying d to f such that the f is substituted by other f. Okay, it also works. So when you do this, this is chain rule, right? Yeah, so you got chain rule as well. Right, using this algebraic definition. Okay, maybe it's a fun exercise if you want to do it. Okay, no limit involved here. No limit. If I give this to first year, should be happier, right? No limit. No limit. Huh? Not happy. You give what to them, they're also not happy. They don't like to do homework. Okay. Okay, so try and you can have an exercise on this. Yeah. So obviously you need to check it on points, right? Because this is function, right? So you need to really check it on point. Let's check it on effects. I think first one is easier, right? Because the way you define it is additive. And then for multiplication one, yeah, maybe you need to do some trick. Okay, then second, we can define an element phi in this du here is called a regular differential form. Okay, this is really coincide with what you have in differential manifold. Okay, so regular form. How many of you taken differential manifold? 1, 2, 3, 4, 4, 5. 子清的时候读 right? I mean differential manifold. Okay, so an element here actually is called regular differential form if for every point in U there exists a neighborhood V and a regular function such that your phi here can be written as a linear combination of dgi. The coefficient here is f1. Okay, and then the set of all regular differentials on U is actually a all U module, so you can multiply any function in all U into it. And then this is what we call a omega 1. Omega 1 of U. What did you know about omega 1 in the other course? These are the one form actually. Okay, actually these are linear form here. These are the one form. Okay. Because only one D there. Okay. Because there's only one D. Okay, makes sense so far? Okay, so for those who haven't taken differential manifold, how do you think about it? Pretty sure you did calculus too. The dx, dy, dz. Okay, something times dx. So for example, the integration you learn, right? Integrate f dx. Actually, you are integrating a form. You are integrating a form. So it's a f times some d or something, dx. So x, you can think of it as another function. So you are integrating a form. So you are no longer like integrate over x minus. You are integrating a form. Okay. This is a general theory about integration. Okay. This one I think we discussed just now. Okay, let's skip. So for example, you can figure out what is the omega 1 of A1. So it's a line. So what's the regular differential form here? So if you go through the argument, it is just C. Okay, if you set your coordinate range as T, so actually it's just D. So it's like on X, on the real line, really you just have dx on there. Okay, any form, regular form that you can define on it is just something times dx. Is it true or not? When you do integration over real variable, it's just something function times dx, right? You won't it's dx squared. Dx squared you also can write in terms of dx, right? 2x times dx. See? Okay, everything can be just as expressed as dx. And this is the point here. And then dx is the element in mx over mx squared. Okay, it's just one dimensional. Okay, and link. And okay. So a general proposition here is let C be a smooth curve and P in C. Then there exists an affine neighborhood of U such that the omega 1 of U is actually isomorphic to OU. Okay, your structure shift applied to this U neighborhood here. Yes, this is kind of nice. This is trying to like recover what you have, what you know about omega 1 of let's say the affine space. So you won't have like dx like d of something very weird thing that you cannot comprehend. So you can always reduce back to the affine. It's okay. Let's skip the proof. Not very enlightening at the moment. Okay, so corollary is if you have a local parameter at point P, then there will exist an affine neighborhood such that gamma 1 of V is equals to OV dt. Okay, so this is the main point we want to introduce this. Obviously, this is only for curve lah. Okay, curve is easier to control because it's just one dimension. So the point here is like we want to study this curve as if how we study A1. Okay. Yeah. So it just really means that locally it's just A1. This is what you did in differential manifold, so right? You study locally. Not locally is a A1. So you can do integration there just like what you did over real. Okay, and then next we'll call what's the rational differential formula. Okay, you can see that this is the equivalent class involving open set again. Okay, so in this class, right, we often like identify elements together if they are agree on some open set. Okay, so this is what we will do on differential formula. And then after we collect all these, this is what we call the set of rational differential form. Okay, so we will get a circle here, round bracket, instead of a square bracket, right? Okay, and then if we do this identification here, should we go through this? No need, this one is just technicality. But the proposition is for curve, right? If you identify all these, element using open set, then it's really just a one-dimensional vector space over the function field. Okay. This is curve, this is not general omega 1. If you change to another variety, maybe it's harder to study. Our variety here is just projective. Okay, one-dimensional. So again, you see one-dimensional. If you see across the pattern, one-dimensional, we can pick out a representative, right? Okay, because everyone is just scalar of it. So if I pick one thing from here, omega here is a non-zero rational differential here. What we call it is a divisor. It is a divisor. Okay, so let me define this divisor for you first. So, okay, so let's take a point around this neighborhood U because this is a rational differential form, right? So we can express it as something times dt. Okay, let's call it g dt here. So since you have g dt here, but this could depend on which point you are at, but every point you could express such as this. And but how you go between this neighborhood? Actually, to go between this neighborhood, right, you need to you could just multiply by a u, which is a unit. Okay, so meaning what? You just need to know how it get expressed in one neighborhood is enough. Because to get to the other neighborhood, you have just multiplied by unit. But just now we already discussed, right? Unit won't affect your status as a divisor because the unit won't contribute zero or pose. Okay, make sense? Does it make sense? Okay, so this divisor here, what we call the canonical divisors. Okay, it's a canonical one. For example, in the projective line, right? I know. In the affine line, right? So the canonical divisor is the dx or the dt, whatever you want to call that variable, the local parameter. Is the dt. Okay. So if you switch to different zeros, it will just be a multiple of that zero. Okay. So this is what we call a canonical divisor. Okay, so how about give an example here? So let's give an example. So if you consider P1 again, take a point, let's say A in A1. Okay, so meaning we take an affine neighborhood around P1. Possible, right? We just don't look at the infinity. Okay, so T minus A is a local parameter here because this is the thing that generate the maximum ideal at A. And then you could ask, how does this dt response at that point? Yeah, how does the dt response at that point? But dt doesn't vanish at this point or not? It doesn't vanish at this point, right? Let me see. Yeah, it doesn't vanish at this point. Okay, so we look at this. So t minus a is our local parameter. Then we want to look at this canonical divisor here, dt. Okay, this is the only thing lived in the gamma one. Sorry, omega one. Okay, dt. So does dt take any zero at at the A point or not? No. Why? Because you should understand this dt as a sum equals to g dt, right? But this g here is constant. Okay, so it doesn't disappear. Okay, so meaning it has no zero at any point at p1. But how about infinity? Okay, let's turn to focus on infinity here. Does dt disappear here or not? Okay, so we know that the local parameter here changed. It's no longer t minus a. Because you want something that vanish at infinity. What can make infinity vanish here? Is 1 over infinity. So the local parameter here is actually t inverse. But how to express dt in terms of t inverse? This is exactly what you do in your calculus. Substitution. Integration by substitution. Okay, so actually I can express dt as minus d square d of 1 over t. 1 over t. This is your integration by substitution, right? Okay, so this is exactly how you express dt inside this in the local parameter of t inverse here. Okay, so you see, you are differ by a how to say this is not scalar, all right? This is what is this by a by factor, yes, by factor. Thank you. Okay, so then you could ask, oh, dt got 0 at infinity or not? Okay, so dt got 0 at infinity or not? Okay. Okay, so the order I put here is -2. Should I put -2 or 2 here? What do you think? Should I put a -2 or 2 here? Should I put a -2 or 2 here? -2 represent poles, right? 2 represents 0, right? So is it a 0 or is it a pole? So if you put infinity here, what happen? Infinity square. So you shoot to infinity. Okay, so this is the pole here. And also that's why you got a -2. Okay, makes sense. Okay, so in this case here, how to express the canonical divisor? So actually you express it as -2 in times infinity. Okay, so this is your canonical divisor. Okay, in this case. Make sense? Okay, so then we'll define the genus, okay, of the curve is defined to be the little L of this canonical divisor. So this is the algebraic genus we define, but if your C is defined over complex number, right, then this is a genus that we count in a topological space. Okay, but in our case, the genus of a smooth curve is equal to the number of linearly independent regular differential forms. And then this form actually build out the topological genus. Okay. Yeah. Should we? Let me see. Actually, we are not far away from Riemann already. Okay. So maybe let's quickly mention first. So if K equals C, this G is equal to the topological genus of the compact Riemann surface C. Okay, so we won't prove this. This is actually getting hard, I guess. Yeah, but just to let you know, this genus that we define actually has relation to the topological genus. Okay, so in the topological genus, right, for example, in this case here, so this genus one, right? Okay, so it says that there's only one linearly um, independent regular differential form that can be it. And then a smooth curve C has genus 0 if and only if it is isomorphic to P1K. Okay, so P1K is genus 0. There's no hole for P1. Okay. And then you can prove the Riemann-Roch theorem here. So Riemann-Roch theorem says what? If C is a projective curve of genus G, okay, so linearly independent regular differential form, and D is a divisor D on C, then there's a relation between these two numbers, LD and LK minus D here. It is differ by 1 plus D minus G. Okay, so I want you to stay on this theorem for a moment. On the left hand side, right, it is just counting the number of linearly independent regular differential form. It's a very algebraic thing. But on the right hand side, it is one. One everyone know since you are born, you should know one. D is the degree of this divisor here. G is another number of differential form. But just now through the theorem that I told you, right? If this theorem put inside a complex case, G actually is a topological property. Okay. So the topological property here tells you something algebraic. Or the algebraic property tell you something in the topological world. Okay or not? Or if you like, if you like, actually this G actually is L of K, right? Okay, L of the canonical divisor. Yeah. Okay, if we play some heuristic thing, so for example, let's say you say LD minus LK minus D, it's like D minus K minus D, right? So minus D, so it's like 2D minus K. So minus K appear on the other side already, but the 2D become like 1 plus D. Let's say this L is linear, let's say. Okay, I don't know if it's true or not, but yeah. I mean, you need to somehow find some way to like remember them. I wouldn't say it's to explain them, but at least you need to find some way to remember them. Because sometimes the way you think about it maybe can generate new maths. Okay. I don't say you can explain it. I just say maybe there's some other way to think about this this relation. Okay. Yeah, this is about Riemann-Roch. Actually, there's some corollary, but maybe not mention it. Any question? This proof, we won't prove it also. Actually, there's a nice book by Guarantee. In that Guarantee, there's a lot of examples. Actually, they can provide a length of a step to prove this Riemann-Roch. I think for the curve case. Yeah, so actually you can follow what he did. Okay, so this is the version of Riemann-Roch for curves, projective curves, where it relates the LD, LK minus D and LK. Yeah, actually, there's another way to think about this theorem is you can put all the L to the other side one. No. Put all the L on the other side and then just equals to 1 plus D. Okay, but the point here, I think they want to relate this LK here to some topological property. There's some real genus counting here. Okay. Any question before we finish the day? Okay, if not, we'll see you tomorrow. Tomorrow is the last day, and we shall take a photo tomorrow.